The application of a 3D rigid body diagram is not much different with the 2D body. So in 3D, as usual, it involves calculation in the Z direction, okay, or the Z axis. So maybe sometimes you can use a scalar formula, but sometimes you may need to use the vector formula, as the free body diagram in a 3D system may be much more complicated to imagine. Similar with the 2D case, the 3D support reaction also depends on the type of connection. So the principle still remains the same lah. If no translational movement are allowed at that particular direction, then there are a reaction force acting at that direction. So I would like to recommend everybody to make a copy or print this particular attachment so that it's easier for you to refer to when constructing the free body diagram. So here are some examples of 3D type of connection. So if you look at this picture and you refer to the attachment given to you in the previous slide, so this type of connection is known as the ball and socket joint. Okay, so kalau tengok kepada attachment yang diberi tu, ball and socket joint would have this kind of support reaction. So accordingly, in our image, we can redraw the reaction force in the X, Y and also Z direction. So if you look at this picture, it's like a bearing actually. So if you refer to the attachment given, so the type of connection for this kind of joint is a single journal bearing. So single journal bearing correspond to the item number 5 in the 3D support reaction. So accordingly, if you refer to that picture, it restrict the movement in the X and the Z direction, and it doesn't allow any kind of rotation in the X and Z direction. So accordingly, if we are to draw the free body diagram of this particular connection, so this is how it would look like. It should correspond to the image given in the attachment. Okay, now let us look at an example on how we can draw the free body diagram for a 3D kind of rigid body. So the first step in drawing the free body diagram in 3D body is usually to identify where is your X, Y and Z. Okay, so for example, in this picture given, X, Y, Z is not defined. So you have to define it yourself. So let's say if this direction is my X or my positive X, and accordingly this direction would be my Y, and definitely the upward direction, which is perpendicular to the XY plane, would be my Z axis. Okay, nice. So bila XYZ is already identified, the next thing is much easier for you to define where is the force acting over here. Okay, so given in the question that A, the joint at A is actually a journal bearing. Okay, kalau you tengok journal bearing, you refer to the attachment given, journal bearing, they can move in the Y direction, but it cannot move in the X direction. So if the movement are restricted in the X direction, definitely there is a support reaction at the X direction. So I'll call it AX. Okay, so dekat Y dia boleh gerak, dekat Z dia tak boleh gerak. It's restricted kan. So accordingly, at the Z direction, it is restricted. There's an additional support reaction force called AZ over there. Okay, that's done. How about point B? So, given in the question that point B is actually a roller. Okay, so kalau roller ni, as usual, it will have only one kind of reaction force, which is it can roll in the X, it can roll in the Y, but it cannot move in the Z direction. So that is a reaction force in the Z direction. So I'm going to call it BZ. Okay, so that's it. So how about point C? So dekat point C, it is given that it is a hinge. Hinge ni macam it's like fixed lah. Dekat X, Y, Z pun dia langsung tak boleh bergerak. So if I were to draw the support reaction, it would look like this. There will be one support reaction at X direction. There will be one support reaction at the Y direction. And there is definitely a support reaction at the Z direction. Okay, so basically all the red lines indicate the support reaction of all the joints of this 3D system. So kalau kita nak redraw the free body diagram, usually you are required to redraw the free body diagram in your answer sheet lah, because every free body diagram would contribute a certain kind of marks. Okay, so the first one, they want you to draw the free body diagram if the weight is neglected. So what is the weight that we consider here? The weight of the board, the body of this board yang kita nak study actually. So the weight is this 400 Newton, which actually act in the middle point of the board. Okay, so if the weight is neglected, kalau kita redraw balik the free body diagram, okay, so of course you can plot the x, y, z like this. Okay, so accordingly you can just redraw the free body diagram by redrawing the support reaction forces that we defined earlier. So if I may go very quick over here, okay, my C is over here, Cx, Cy, and also Cz. Okay, if the weight is neglected, then I don't have to draw this 400 Newton. But if the weight is considered, then I have to draw the 400 Newton force acting downward. That's simply it. Okay, so dah siap. Okay, now let us try to solve the calculation process of equilibrium for a 3D rigid body. So given a homogeneous plate with a mass of 100 kilogram as shown, okay, so mass are usually acting downward. So if I were to redraw the direction of the mass and the position of the mass, it would usually be exerted exactly in the middle of a body. So in this case, it will be exactly in the middle of the 3 meter, which is 3 meter kalau bahagi 2, it will become 1.5 meter, and 2 meter kalau bahagi 2, it will become 1 meter. So it will be exactly at this particular point. So if I were to draw the line of the weight, okay, so recall the formula for weight is equals to mass multiplied with gravitational acceleration, and we know that our mass given is 100 kilogram and gravitational acceleration is 9.81 meter per second squared. So if you multiply these two values, you get 981 Newton of weight. Okay, so that is one thing. Okay, the next thing is that if you notice, this 3D body does not define where is the x, y, and z axis. So similar with the previous example, we have to first define where is our x, where is our y, and where is our z. So as usual, I would like to use this particular line as my x-axis, this line as my y-axis, and this upward line as my z-axis. Oops, it overlapped with my calculation, but then I hope you understand my point. Okay, now if I were to redraw the 3D free body diagram of this particular plate, okay, probably it would look something like this. Okay, so if I were to redraw again the axis accordingly, so this would be my x, this direction would be my y, and the upward direction would be my z. Okay, so now we need to draw the support reaction at each joint. So again, given in the question that there is a joint of roller at point A, which is over here. So if you look at the attachment given to you, for a roller kind of support, it will only have one reaction along the z direction. You see, roller ni dia macam roda. It can move in the z direction. It can move in the x direction, it can move in the y direction, but it cannot move in the z direction. So meaning there is a corresponding force acting on the z direction, and we are going to call it AZ. Okay, now that's done. So let's look at other type of joints exist in this particular system. So there is a ball and socket joint at P. So again, if you look at the attachment given, the support reaction for a 3D plane, for a ball and socket kind of joint, it restrict movement in all the x, y and z direction. Okay, so if I were to redraw the corresponding support reaction forces, there will be one support reaction in the x direction, so I'm going to call it bx. There is another restriction in the y direction, and I'm going to call it by, and there is another reaction at the z direction, and I'm going to call it bz. Okay, so now that is done. Okay, this is point A, this is point B. Okay, so now what are the type of support available in the system? So dia kata dekat point C there's a cord. So usually if there's a cord, it means that there is a tension force at the cord acting on the direction of the cord. So basically the direction of the cord is the z direction in our system. So there is one tension force over here, and we are going to call it CZ because it happens along the z direction. Okay, so is there any other support joints at the system? Dah habis dah. The ABC we already defined in our free body diagram. The next thing is we need to redraw all the forces acting on this particular body. For example, there is a downward force of 300 Newton. So, tarik dia ke bawah, 300 Newton. Okay, and don't forget there is a weight of the plate acting exactly in the middle of the plate. Okay, so this is our W and the magnitude is 981 Newton. Okay, now don't forget there is another magnitude defined in your 3D system. So if you look at this highlighted area, okay, you notice there is a moment acting along the negative y direction. So if I may redraw this moment with a different color so that I don't miss it out during my calculation. So I'm going to like draw the moment axis. This is the moment axis, tebal-tebal ni. Okay, so if I use my right hand punya rule, the direction of my moment axis moment would be over here, and the magnitude of my moment along the y direction, negative y direction, actually is 200 Newton meter. Okay, so now all the reaction forces are defined in my 3D system. Now only I can apply the calculation of equilibrium for this 3D rigid body. Okay, so as usual, if I were to zoom this up, okay, so as usual, the solution involve we assuming the system in equilibrium, in a balanced state. Okay, so approach things systematically. I like to start with finding what is the summation of all the forces in x direction. So all the forces must be equivalent to 0. So what are the forces exist in x direction? So this is our x-axis. So the forces exist in x direction is bx, and oh, that's it. So cool. So now if you are to rewrite the magnitude over here, there is only one bx, which is directed positive to the positive side of our x over here, is equivalent to 0 Newton. So as there are only one variable over here, so we can definitely confidently say that the magnitude of bx is 0. Okay, now we continue our equilibrium condition in the y direction. So summation of all forces is equivalent to 0. So now let us see what are the forces exist in y direction. Let me use a different color. Okay, so this is my y-axis. So the forces exist in y direction is by, and oh, that's it. Cool. So again, if we are to rewrite the magnitude of forces in y direction of by, so by, we can confidently say it is 0 Newton as well. Okay, so bx is done, by is done. Okay, the next thing is, let us, as this is a 3D system, definitely we need to calculate the summation of forces in z direction. Okay, this time around it involves the calculation of forces in z direction. So now let's see what are the forces happening in the z direction. So this one is z over here. okay, and then there's one BZ over here, there's one CZ over here, and there's a downward force of 300 Newton and 981 Newton. So there are 5 forces acting in the x direction, and let's translate all that forces into our equation, whereby our AZ is positive, and then there's another BZ magnitude, so we have to plus because it's pointed upward, and then there's another CZ plus with CZ, and then we have to minus with the 300 Newton, don't forget this one, and we have to minus with the weight of the plate, which is 981 Newton. So it's pointed downward, so that's why it's negative. So there are 5 items in our equation, okay, correct? So all this would be equivalent to 0. So if we, as usual, the strategy is to place all the unknowns, which is AZ plus BZ plus CZ on the left side of our equation, will be equivalent to, so bring this to the right side, this would become 1281. Okay, now we are not done yet because there are 3 unknowns this time around, so let's just call this to be equation number 1. Okay, now as we cannot solve all our unknowns using the summation of forces, then we have to calculate the moment, the summation of moment in our equation. So in a 3D system, we need to calculate what is the summation of moment which rotate along an axis. Okay, so the summation of moment in the x-axis should be equivalent to 0. So tengok, let me just highlight mana x-axis kita. Okay, so let's use like a different color. Is green used? Okay, let's use grey lah this time around. Okay, so this is my x-axis kan. I can also measure along the x direction which passes through point B juga. Okay, you see the direction is the same. Okay, this x, this is also x actually, except that it is translated. So like my previous strategy in the 2D rigid body, I like to calculate moment at a point where there are many forces acting on it. So if you look at this line that I highlighted here, it's becoming almost black here. There are many forces acting on this particular axis. So I like to use that as a reference point for my rotation, as it can cancel out many unknown magnitudes and it can ease out your calculation process. Okay, so in this case, I'm going to use this one, this line, as my x-axis reference. Okay, so now maybe I need to put a remark over here, measured at BC axis. Okay, so it's still x-axis. Okay, now so kita tengok what are the forces which will create rotation. So again, if you recall, the formula for moment is equals to F multiplied with T. Okay, so there is one force over here which is our AZ value. Okay, so now AZ, if I were to rewrite the expression AZ, it have to multiply with the perpendicular distance from the force of line to the axis. So it will be this distance, and if you refer to your figure, the distance is 2 meter. Okay, now the question is, what is the direction of this force? If you want to know the direction of your force, you use the right hand rule. Okay, whereby imagine like this axis as a rod, and then your finger too is gripping on the rod. 1, 2, 3, 4. I know my drawing is really bad, and this would be my thumb. Okay, so my thumb is pointed towards the negative x direction. So it means the expression over here, the AZ multiplied with 2, is negative. Okay, that's how I imagine the rotation of my moment in a 3D system. I just use my right hand rule. Sometimes bila you nak imagine whether it is clockwise ke counterclockwise, it becomes a bit tricky in a 3D system. So you just use your right hand rule. You imagine macam you genggam the axis and the finger the direction of your thumb is the direction of that particular moment. Okay, so kalau AZ ni dia macam ke atas tu, so kalau you genggam dia following the direction of AZ, genggam this axis, you will notice the direction of the thumb is on the opposite side, so that's why it's become negative. Okay, now how about force Bx, By and Bz? So all these forces passes through the rotation axis that we want to study. So if it passes through the rotation axis, then there are no D. When there are no D, it means there are no moment produced by this particular force. So we can actually cancel out or ignore the calculation of moment caused by Bx, By and Bz. Okay, now what are other forces that we can cancel out? We can also cancel out the force caused by CZ juga, because it passes through the rotation axis that we are studying. Okay, now what are other forces exist in x direction? So let's look. There's a 300 Newton over here. So 300 Newton, and the perpendicular distance from the 300 Newton to our line of force is again 2 meter. Okay, so this time around, what is the direction of this moment? So if you use your right hand finger rule, it will create a counterclockwise motion, so it will be a positive direction. Okay, so how about this 981? Accordingly, 981 is the same direction as 300 Newton, so it become plus 981, and the distance from 981 Newton to this axis is, looking back at the picture, it would be a distance of 1 meter. Okay, so we put that value into our D, and then what are the other forces which will create moment in the x direction? Oh, tak ada. So it will sum up to 0. So as you can see, there is only one variable or one unknown in this particular equation, which is AZ. So we can directly solve this equation, whereby AZ is equivalent to, so this 300 and 981 ni kita bawa ke kanan, divided with negative 2, we will get a corresponding value of 790.5 Newton. So cool. So the magnitude of AZ is done. Okay, since there are still unknowns in the support reaction forces, we can continue our calculation process by calculating the moment in the y-axis pula. So summation of all the moment in the y-axis should be equivalent to 0. So I am going to take this particular line as my y-axis, and I will put a remark that my y-axis is measured from point A to point B, so that I can cancel out many other forces over here. Okay, let's start with the first force, which is the 300 Newton, and then we have to multiply with the perpendicular distance to the rotation axis, which is this side. So if you look at the original picture given, the distance would be 1.5 meter. Now, what is the direction of this particular moment? So if you use your right hand rule, the direction of 300 Newton, kalau you genggam dekat the y-axis, would be pointed towards the negative side. So this would be negative. Okay, so that's 981 Newton, and the perpendicular distance to the rotation axis, if you refer to the original picture, will be exactly in the middle, which is 1.5 meter. And again, the magnitude of this particular moment is negative. Okay, what else are there in our 3D system? Oh, okay. Don't forget for this moment over here, it happens along the y-axis. So you include that 200 Newton meter moment into your equation as well. And if you notice, the direction of this particular moment is pointed towards the negative y direction. So the magnitude is negative. So what else is there? Okay, there's a CZ over there. So CZ have to multiply with the perpendicular distance. If you refer to the original picture, the perpendicular distance would be 3 meter. So the direction is upward. Use your right hand rule. It will be a positive magnitude. So as there are only one unknowns in this equation, you can actually solve for the magnitude of CZ, whereby you rearrange the expression in your equation, and you will get the magnitude of CZ to be 707.17 Newton. Okay, now your AZ is known, your CZ is known. There is only one magnitude is left, which is the BZ value. So you don't have to proceed your calculation for the moment along the Z-axis pula. You can just substitute the value of AZ, which you get earlier, and the value of CZ of 707.7 Newton into equation number 1. So from equation 1, AZ is 790.5 Newton plus with BZ, BZ is still unknown, plus with CZ, which we already calculated earlier to be 707.17. So the summation of all these three magnitudes will be equivalent to 1281. So you can easily solve for BZ, and the final magnitude of BZ would be negative 216.67 Newton. Okay, so now the question is, do you need to rewrite this expression in a positive value? Not necessarily. Okay, not necessarily. You can just leave your answer as it is in a negative value. But what's important is that you indicate the initial direction that you assume in the free body diagram, so that I can cross check whether your magnitude ni betul ke tak, and I can cross check whether it is opposite to the initial assumption. Okay, so again, I would like to emphasize that it is not necessary that you define this magnitude as a positive value. What's important is that you indicate the initial assumption of your force, the direction of your force in the free body diagram. That is the most important thing. Okay, bye-bye. Okay. Okay, that is all for now. We actually managed to cover the topic of equilibrium of rigid body. So the bottom line is you need to really understand on how you need to construct the free body diagram of the force and the moment system. Okay, you have to consider the external forces as well as the support reaction forces. So direction of force and moment during the construction of the free body diagram may not be that crucial because it's an initial assumption, kan? Nama pun assumption. But the main deciding factor which confirms the direction of your assumption tu is the calculation. If you get the calculation right, then the direction of your force diagram, the direction of the forces and the moment would be accurate lah. Okay, so please practice a lot on this topic because it is a very popular question in many statics exams. Until then, they're making so much noise over there. All the best and see you later, alligator.